So hopefully you're starting to get the hang of what linear modeling is capable of and what exactly it does. And if you're not yet, that's okay. We're going to work through another example here. Let's make a new subset of the BARMOS1 data. We're going to call it BARM data sub 2, in contrast to just BARM data sub that we had before. Let's pull out from the BARMOS1 data frame all of the artifacts, which is their names are listed in the label, all of the artifacts that are flake axes, or the artifacts that are denticulated / notched pieces. Remember to put a comma here because that's referring to the rows, and we want all the columns. So let's run that. Now if we inspect BARM data sub 2, our output shows us that we've got the denticulated and notched pieces, and we've got the flake axes with their northing and easting coordinates there in the first two columns. And so with these data, let's again plot the northing against the easting. And let's just do it for the first BARM data sub 2 for the first artifact type, flake axes. So the label is equal to flake axes, and we have to put a comma there. So now we're plotting the northing values as a function of the easting values, and the data that we're using for this is not just the entire BARM data 2, but we're indexing within that for just the flake axes. So if we plot this, we end up with another nice kind of map of the northing and easting coordinates for these artifacts. And so now let's plot, this time, the points. I'll copy the plot function, but I'll change the plot function to the points function and change flake axes to denticulated / notched pieces. And I want to add that color argument to separate them. Color equals red. So now that I've done this, you can see that we've got the flake axes in black, the DN pieces in red, and the distribution of these artifact types across this site. Now, let's see what the difference in the easting coordinates is for these different artifact types again. Perhaps there's a reason that we think that there's some east-west trend across the site in the distribution of these two artifact types. We can plot these east values as a function of label for the BARM data sub 2. In this case, again, we're going to want to put as numeric around the label because the label is a character, and we want to turn it into numeric 1 and 2 values. If we plot this, here's our data. This is what we're going to build a model based on. These are our easting coordinates for the first artifact type, the easting coordinate for the second artifact type. It looks like there's a bit of a trend here in the easting coordinates, that they're higher for this other artifact type. And so to then build this model, we proceed the same as we did before. Let's create an object, use the lm function, lm east as a function of label, data equals barm.data.sub2. And if we run this, we now have our model. Now again, before we proceed with exploring what this model means and how to interpret it, we need to run the diagnostic plots and make sure that everything looks good. So if we plot mod 2 and run that, now we go down to the R console and hit enter, and that brings up the first plot. Our residuals That red line should follow that dotted line horizontally. It moves upwards a little bit, but not terribly, and the residuals are still pretty spread out around values of 0. They're a little bit more negative in the first case. That's why that red line is a little bit lower down there. But this isn't egregious. We could still get by with saying that our residuals look like they're more or less conforming to the assumptions of a linear model. If we then look at the next plot, the QQ plot, this is the expression of whether the residuals are normally distributed. And in this case, we're starting to deviate from normality a bit. There's still a lot of values right along that dotted line, but especially up here at the positive values, this is probably a bit problematic. It might not be. You could still survive and make this model and get by and be able to interpret it. But we're starting to get into the territory here where this is deviating a bit much for my comfort level. Again, this is very subjective. The more of these you see, the better you'll get at identifying what problems might be. But in this case, we're going to proceed as if this were really normally distributed. And indeed, it might not be problematic in the grand scheme of things. You'll recall that normality of residuals is perhaps one of the least important assumptions of linear modeling. We can survive even if we deviate from that assumption a little bit. Let's look at the next plot. We've got our standardized residuals, just transformed residuals so that they're all positive values, and the fitted values on the x-axis. It looks like the trend in the residuals is a bit downward. So as the fitted values increase, the kind of trend in the residuals here is a bit downward. So they're not perfectly spread around the different, around the best fit line, around the fitted model line. But again, this isn't necessarily egregious, and we can still survive with this. And then the final plot, looking at any leverage of the points, doesn't seem like much is going on here. We don't have any strong outliers. Otherwise, we would see these red confidence intervals on the plot. Again, if interpreting all of this isn't clear, you're not sure what good plots and bad plots look like at this point, that's absolutely normal. It takes a long time to wrap your head around these. There's, again, a lot of help files that you can read on the internet about interpreting these diagnostic plots. And as we proceed in this module, you will see what diagnostic plots look like that really deviate from the assumptions, and in cases where we very clearly cannot proceed any further. In this case, we're going to proceed. Even though that QQ plot didn't look all that great, we're going to act as if it did for the purposes of illustrating what's going on here with this model. So, we've interpreted our diagnostic plots. Things look okay. We're going to say that they look good. And now, summary mod 2. Now we're going to inspect the model itself. As I said, you've got some information up here at the top, the formula itself, some breakdown of the residuals, but the coefficients section is what we really care about. It's getting a little split over different lines here. The coefficients section, we've got the intercept, and then we've got the denticulated and notched pieces. So because we're looking at flake axes and DN pieces, the flake axes are being assigned to the intercept here. And we know, based on the equation of a linear model, right, thinking back to your grade school math classes, y equals mx plus b, or y equals beta 0, the intercept, plus beta 1, the slope, times your data x. In this case, what that equation really looks like is what we're trying to predict, y, is equal to the intercept, 5.4125, plus the slope, 1.371, times x, times what is on our x-axis. That's the equation for this linear model that we've just built. And in this case, as I said before, because we've got two different groups of data, flake axes and DN pieces, R is treating flake axes as the intercept. That means that's group 0. And so x in this equation becomes 0, which cancels out the slope, and so the mean predicted value of flake axes, the easting coordinate that we're looking at, is 5.4125. With group 2, the denticulated and notched pieces, group 1, it's our second group, but R is numbering these as 0 and 1, that becomes a value of 1. And so when you multiply the slope times 1, you get the slope, and so you need to add 5.4125 plus 1.371. And that right there, a value of 6.78, that is the estimated mean easting value for denticulated and notched pieces. So we've got values of 5.4 and 6.8 for these two different artifact types and their easting values. Looking at the p-values then, right, we've got, it looks like the estimate of the intercept is significantly different from 0, but this really doesn't matter. That p-value there is hardly ever meaningful, and you hardly ever need to pay attention to it. That's not a concern of ours. The intercept could be very negative, it could be very positive, it could be right on 0. That doesn't matter for the statistical analysis that we're running. What matters are the other p-values and the overall model p-value. And so when we look at the p-value for denticulated and notched pieces, this estimate of 1.37 plus or minus 0.58 turns out to be significantly different from 0. And generally, that p-value there doesn't really matter. In a lot of the models that we're going to run in the future, you won't look at this p-value, but in this case, it is the same as the overall model p-value, which is reported down here at the end of the summary output. And the reason for this is simply because, as I said, the intercept is group 0. And so we're comparing this intercept effectively to a value of 0, and it happens to be significantly different from 0 based on the standard error around it and the t-distribution that we're comparing it to. So our p-value is 0.226, and you can see it down here for the overall model as well. This means that there is a 2.2% chance that we would observe these easting coordinates for flake axes and denticulated notched pieces if the null hypothesis were true and they were actually distributed identically. Now, you may not have realized it, but what we just did is actually a t-test. A t-test is simply a linear model where you're comparing two different sets of values between two different groups or two different categories. This is kind of a very basic statistical test that's important for you to be aware of. And this illustrates the point that pretty much every statistical hypothesis test is some sort of variant of a regular linear model. Linear modeling truly is the foundation for all of these sorts of inferential statistics that we're doing. So remembering this kind of linear model equation is really important for unpacking what is happening here. If you don't want to go through that whole process of building a formal linear model and interpreting that way, there is a t-test function in R that you can use. If you type t.test, you can inspect the help file for that. Here we're going to run east as a function of label. So the easting coordinates is a function of the label. We've got the flake axes and the denticulated and notched pieces. I'm going to say data is equal to barm data sub 2. And here we're going to specify that the variance is equal between the two different groups. var.equal equals t, that argument there. If we run this, we see our output. T equals negative 2.349. The degrees of freedom is 52, and the p-value is 0.226. Hopefully that p-value sounds familiar to you, because if you'll recall, it's the same thing as the p-value from our model here, the same value as for the estimate being different from 0 for our slope, the value of denticulated and notched pieces. So this is identical. What we did was a t-test. We'll pull up that output again. This t-test is comparing the mean easting value between these two groups, flake axes and denticulated and notched pieces. The t-test function here includes a calculation of the estimated mean for each of the two groups down here at the bottom, which is very handy. I showed you how to do it by hand above, where the intercept is simply 5.4125, and if you add it to the slope, you get the estimated mean for the second group, 6.78, right? Again, it's identical. What I just showed you doing the linear model way is the same as using this t-test function, because the t-test function is simply kind of a wrapper on that LM function with some extra stuff. But so when you're looking at this t-test output, you can see that the three main things that you need to report are your t-value, your degrees of freedom, and your p-value. So when you run an analysis like this, and you're reporting on your results, you would say something like the results of a t-test indicates that there is a significant difference in Easting values between these two artifact types. A statement like that, and then in parentheses you would say t equals negative 2.3496. Provide your t value that's shown right here in that t-test output, right there. And then supply your degrees of freedom, because again, the degrees of freedom in this case is being used as in conjunction with the t value to calculate your p value. So you always need to supply the degrees of freedom. And in this case, if we look at BARM data sub 2, I'm going to go down here into the R console and use the nrow function, the number of rows of BARM data dot sub 2. It's 54. That's the number of observations we have. That's our sample size. Notice that the t-test output is showing us that our degrees of freedom is 52. And that's because we've got two parameters in our model, an intercept and a slope. Those two parameters are burning a degree of freedom each. So 54, our sample size, minus 2 is 52, our degrees of freedom for this test. Again, if you're still not clear on that, it's okay. Just know that you need to report it. Report your t-value, report your degrees of freedom. And because our p-value is 0.02, that's significant. And it's significant at the 0.05 level. And so that is how you would report the results of this t-test, of this linear model on these two groups of data. The result of a t-test indicates that there is a significant difference in Easting values between these two artifact types. The t value, the degrees of freedom, and your p value at the significance threshold that's most relevant for it.